I want to thank the organizers for providing me this opportunity. Let me begin by giving a brief overview of the topics that I will be talking about. We know that ordinary symmetries of spaces are usually described by group actions. Now, given a subfactor or an inclusion of two factors, their standard invariants are group-like objects which encode quantum symmetry. Now, the study of the standard invariants, they have got wide applications in various areas of maths and physics. Some of them are in the study of invariant of knots and links, Jones polynomial, topological quantum field theory, conformal field theory, and topological physics of matter. One such description of standard invariant is given by what is known as Q systems, and they can be thought of as categorical version of Frobenius algebras. Now, I will be talking about Q systems in the second part of my talk. And in today's lecture, so first I will take you through some of the basic results and definitions. Then I will discuss some of our results. Okay, so to begin with, so before I define what is a sister tensor category, let me start with some examples. So we start with the easiest one, the category of finite dimensional Hilbert spaces, where the objects are finite dimensional Hilbert spaces and morphisms are linear maps between them. And in this case, the tensor structure is given by the usual Hilbert space tensor product. In the second example, consider any compact quantum two, and consider the representation category whose objects are finite dimensional unitary representations and whose morphisms are interplanars. And in this case, the tensor structure is given by this link numbering notation. So some of you might already be familiar with this. So nevertheless, let me give a quick description. Okay. Take the unitary algebra. Okay. And say x small x equal to x1 tensor x2. Be an element which transfer x. Okay. Then the element x1 is defined as x1, x2, 1. This is an element of x inside 3 times. So similarly, the element x2 3 is defined as x1 x. So this is roughly the link numbering notation, and that is how the tensor structure is defined for this category, representation category. In the third example, consider any sister algebra and consider the category whose objects are right AA correspondences and whose morphisms are adjointable AA linear maps. In this case, the tensor structure is given by the relative tensor product, and finally we have the standard invariant of a subfactor. Now let me quickly define what is a sister tensor category. Now, sister tensor category is a category such that all the home spaces, they are finite dimensional vector spaces. For every pair of objects, we have an adjoint map denoted by star, which reverses the direction of the arrows and which is contravariant in the sense that G compose F star is F star compose G star, and F double star is F for all morphisms F, and all endomorphism spaces are sister algebras with respect to this adjoint operation. And all finite directions and sub-objects exist. And there is a distinguished object denoted by 1, which acts as the unit of the tensor product. And finally, you have a tensor functor from C cross C to C such that F tensor G star is A star tensor G star for every morphism F and G, along with unitary coherence isomorphisms, where alpha is the associator, lambda is the left uniter, and rho is the right uniter. Okay, now all these examples, except example number 3, satisfy one more condition in addition to being a sister tensor category, which is the existence of dual objects. So those sister tensor categories in which every object has a dual object will be called rigid sister tensor category. So that is what we define next. So a sister tensor category C is said to be rigid if for every object X we have a triplet X bar or R bar, where R is a morphism from 1 to X bar tensor X and R bar is a morphism from 1 to X tensor X bar, satisfying these equations. So these equations are called the conjugate equations, and we say that the pair R bar is a solution of these conjugate equations. And the object X bar is called the dual object of X, and it can be shown that it is unique up to isomorphism. Okay. Now let me define subfactor and standard invariants. Now, 2-1 factor is an infinite dimensional polynomial algebra having a trivial center and having a unit faithful normal tracial state. One quick example is the group one Riemann algebra of the group of those bijections of natural numbers which fixes all but finitely many elements. Now, a subfactor is an unit inclusion of two unfactors. Now, a subfactor n inside M is said to be a finite index if M has a finite n basis. Okay, now suppose n inside M be a finite index subfactor. Then consider L to Mn be the rigid sister tensor category generated by L to M as an NN bimodule. Then the standard invariant of this inclusion is defined as the pair where the first component is given by the rigid sister tensor category generated by L to M, and the second component is given by L to M, where L to M is viewed as an algebra object in this category. Okay. Now, suppose X be the NM bimodule L to M, then it can be shown that the dual object of X is given by L but viewed as an MN bimodule. Now, the data of the standard invariant is basically given by this grid of finite dimensional sister algebras. Now, all these sister algebras, they are finite dimensional because the subfactor that we started with is a finite index. And our goal is to study this grid under the lens of two categories. So now let me quickly define what is a two category, and then I will talk about the graphical calculus associated to two categories. Now, tensor category is basically a two category with only one object. Now, a two category, naively speaking, consists of a collection of zero cells, also known as objects, one cells and two cells, along with compatibility axioms of a tensor category. Now, let me give some examples of two categories. So first, we have the two categories of sister algebras, where the zero cells are sister algebras, one cells are right correspondences, and two cells are adjoint intertwiners. Then we have the two categories of categories, where the zero cells are categories, one cells are functors, and two cells are natural transformations. Okay, so let me now talk about the graphical calculus. So we will use some pictures, and in the pictures, zero cells will be denoted by regions, one cells by strands, and two cells by boxes with strands passing through it. Now let me explain this through some examples. Okay. Now say we have two zero cells A and B, and say x1, x2, b2 one cells from A to B, and f be a two cells from x1 to x2. Then this diagram will represent the two cell F. Okay. Now suppose we have two cells F and G. Then their tensor product is obtained by placing these boxes side by side. So this diagram will represent the two cell F tensor G. Now suppose we have two composable two cells F and G, and then the composition is obtained by placing these boxes one upon another. So this diagram will represent the two cell G compose F. And one more additional example. So suppose we have three two cells F, G, and H, such that H composed with F tensor G is well defined. Then this diagram will represent the two cell H composed with F tensor G. So this is roughly the graphical calculus for two categories. Now, using this graphical calculus, I will explain the notion of duality in the context of two categories. So say we have a one cell X. Then this one cell X is said to be dualizable if you have another one cell X bar in the opposite direction, along with these two cells rho and rho bar, which you do not pictorially by these arcs. And these two arcs, they satisfy these equations. So these equations are those conjugate equations that was defined in the context of rigid sister tensor categories. So one cell X is said to be dualizable if you have another one cell X bar in the opposite direction, along with these two arcs satisfying these equations. Okay, now in part one, we try to capture the model of this grid of finite dimensional sister algebras in the context of two categories. So the basic idea is to replace these finite dimensional sister algebras by finite sister semi-simple categories. Now by finite, I mean that there are only finitely many isomorphism classes of simple objects. So we replace this finite dimensional sister algebras by finite sister semi-simple categories. These canonical inclusions by star linear functors, and commutativity of the squares by suitable natural unitaries. And we have encoded all this information in two categories, which we'll call as UC, and it is an acronym of the term unitary connections. So now let's describe these two category UC. So now to define this two category UC, you have to define it zero cells, one cells, and two cells. So we start with zero cells. So the zero cells, they will consist of chains of finite system simple categories, where each gamma k is a star linear function. And we'll denote the zero cells by gamma dot m dot. Okay. Now we define one cells. So suppose we have two zero cells, gamma and deltas, then one cells between them will consist of sequences lambda I, where each lambda I is a star linear function from mi to ni, and each wi is a unitary natural transformation from delta I plus 1 lambda I to lambda I plus 1 gamma I plus 1. And these wi's are called unitary connections. And from now onwards, I will use the graphical calculus for the two category of categories, meaning I represent functors by strands and natural transformation between functors by boxes with strands passing through it. So pictorially, we'll denote the functors lambda i's by colored strands and other functors by black strands. And pictorially, we denote the unitary connection wk by this diagram. And we'll denote the one cells by lambda dot. Okay, now we define two cells. So suppose we have two one cells, lambda and lambda tildes, then two cells between them will consist of sequences eta case, where each eta k is a natural transformation from lambda k to lambda k tilde, such that this equation is satisfied eventually from some level L. Now this equation is called the exchange relation, and we say that the pair eta k plus 1 satisfy exchange relation eventually from some level. Okay, now we provide a realization of these two category UC in terms of right correspondences. So basically, we build a two functor psi from UC to the two category of right correspondence over AFD pre-sister algebras. Now, by a pre-sister algebra, I mean that it is a star algebra which satisfy all the axioms of a sister algebra, except that it might not be complete with respect to the norm. Now, to define this two functor psi, we have to define psi on the zero cells, one cells, and two cells. So we start with zero cells. So suppose we have a zero cell, gamma dot m dot in UC. So now take the object m0, which is defined as direct sum of all irreducibles in script m0. Okay, now by irreducibles of a category, I mean representatives of each isomorphism class of simple objects. And throughout our discussion, I will fix the set of those representatives. And since we are dealing with finite semi-simple categories, that means we have only finitely many irreducibles. So this direct sum is a finite direct sum. So m0 is the well-defined object in script m0. Okay, now take ak to be the endomorphism of gamma k up to gamma 1 m0. And we have canonical inclusions of ak inside ak plus 1. And using these inclusions, we define psi 0 of zero cell gamma dot to be a infinity, which is defined as union of ak's. And now we have to define psi on the one cells. So suppose we have two zero cells, gamma and deltas. So first we apply psi on these two zero cells and obtain a infinity and b infinity. And say lambda be a one cell from gamma to deltas. So we have to define psi 1 of lambda dot. Okay. So before we define psi 1 of lambda dot, we define the space hk to be the space of morphisms from delta k up to delta 1 n0 to lambda k gamma k up to gamma 1 n0. And it will turn out that each hk becomes an ak bk bimodal, where the actions of ak and bk are given in this way. Also, hk has a bk value inner product, where the inner product of xi comma zeta is given by zeta star composed with xi. Now the unitary connections, they induce canonical inclusions of hk inside hk plus 1, and we have this result that all these inclusions and the corresponding actions and the right inner product are compatible in the obvious sense. So using this lemma, we define h infinity to be the union of hk's, and it turns out that h infinity is a right a infinity b infinity correspondence. And we define psi of one of this one cell lambda to be this h infinity. So now we have to define psi on two cells. So say we have two one cells, lambda and lambda tildes, and eta k be a two cell from lambda to lambda tildes. So first we apply psi on lambda tilde and obtain h infinity tilde. Now suppose capital K is the level from which this sequence starts satisfying those exchange relations. Then for those small k greater than capital K's, we define the maps Tk from Hk to Hk tilde, where the maps are given by so xi going to eta k of gamma k up to gamma 1 m0 composed with xi. And it will turn out that each of these maps, Tks, they are AK-BK linear maps, and the exchange relation of eta k and eta k plus 1 will yield that Tk plus 1 restricted to Hk is given by Tk. And we define psi2 of this two cell eta k to be the operator T from H infinity to H infinity tilde, where the map T restricted to Hk is given by Tk. And it turns out that T will be an adjointable A infinity B infinity linear. Conversely, it can be shown that every interdeterminant from H infinity to H infinity tilde comes from a two cell in UC. So we have this theorem that psi is a two functor which is fully faithful at the level of two cells. Okay. So now, since we have obtained the realization of UC in terms of right correspondences, so now the question is, can we take a double star completion of UC and provide a realization into the two category of one-dimensional algebras? Now, by double star completion of UC, I mean whether there is a bigger two category, which is a double star two category, and which contains a copy of UC. Now, to answer this question, we need some more information, and the extra information that we need are weight functions on the set of irreducibles of those finite semi-simple categories. So as before, we will run the previous program with weighted finite sister semi-simple categories. Now, before I proceed further, observe that given any finite sister semi-simple category M, and for any irreducible V, and for any object X, the space of morphisms from V to X becomes a Hilbert space, where the inner product of sigma comma tau is given by tau star composed with sigma. Now, using this inner product and using this weight function, one can obtain the following functionals on each morphism space, where the functional trace x on end x is given by this equation, and it will turn out that each of these functionals trace x becomes a faithful positive linear functional. Moreover, this family of functionals, they form a categorical trace, which means that trace x of alpha beta is equal to trace y of beta alpha, where alpha is a morphism from y to x and beta is a morphism from x to y. Okay, now using all this, we define the two category of tracial unitary connections. Okay, so now we describe these two category of tracial unitary connections. So as before, the zero cells, they will consist of chains of weighted finite sister semi-simple categories, where each gamma k, in addition to being star linear functor, the adjoint of gamma k's should also satisfy this condition that gamma k prime mu k is equal to mu k minus 1. Okay. Now suppose we have two zero cells, delta and gammas, then one cells in UC trace will consist of those one cells in UC, such that this boundedness condition is satisfied for every k. Okay. So now we have to define two cells. Now for defining two cells in UC trace, we need some mode tools. And the extra tool that we need is something which you have termed as the loop operator. Okay. So suppose we have two one cells, lambda and lambda tildes. Then the loop operator from lambda to lambda tilde is defined as a sequence of maps SKs, where each SK is a map from the space of natural transformations from lambda k to lambda k tilde to the space of natural transformations from lambda k minus 1 to lambda k minus 1 tilde, where the maps SKs on eta is defined using this diagram. Now in this diagram, these crossings, they come from the unitary connections of lambda and lambda tildes, and these arcs, they come from the solution to conjugate equations of the functors delta k's. Now using this loop operator, we define the two cells. So two cells in UC trace from lambda to lambda tilde will consist of norm-bounded sequences eta k's, where each eta k is a natural transformation from lambda k to lambda k tilde, such that sk eta k is equal to eta k minus 1 for every k. And so these are the two cells, and it can be shown that two cells in UC extend to a unique two cell in UC trace. So we have this theorem that we have a two function from UC trace into the two category of hyperfinite von Neumann algebras, which is fully faithful at the level of two cells. Now, the construction of this two functor is almost similar to the construction of the two functor that I described in the case of unitary connections. Okay, so now, so this completes part one. So, are there any questions from part one? Yeah, yeah.
Can you motivate the user to category? The tensor category is one category.
Okay, so actually we are trying to construct. So the main motivation was to construct hyperfinite von Neumann algebras from those towers of algebras that don't come from the basic construction. So we have taken this to a more general setup. So we did it in the context of two categories. And another motivation I would like to say is that, so as of now, the construction of hyperfinite von Neumann algebras from tower of algebras using the basic construction. So in most of the contexts, the construction was done using bi-unitary connections, right? So we tried to skip the bi-unitary part and we constructed these hyperfinite von Neumann algebras using only unitarity of the connections. So that is one of the motivation. Okay. So now part two. So part two is about Q system. Okay. Now first I will define what is a Q system. Then I will give some examples. So suppose C be a start to category. Now by a start to category, I mean that is a in which the category of one cells form star categories. Okay. So given a start to category C, a Q system in C is a one cell Q along with multiplication and unit maps, where you represent the multiplication unit maps graphically in this way, and their adjoints, they are represented graphically in this way. Now, these maps, they need to satisfy the following properties for Q to be a Q system. So the first condition is the associativity condition. The second condition is the unitarity condition. The third condition is the Frobenius condition. And finally, we have the separability condition. Okay, now let me give some examples. So suppose we be a finite dimensional Hilbert space and say E1 up to En be an orthonormal basis, and say E1 bar up to En bar be the corresponding dual basis of V star. Now these basis vectors, they use the following evaluation and co-evaluation maps, and using this evaluation and co-evaluation maps, it will turn out that V tensor V star is a Q system where the multiplication map is given by identity of V tensor with evaluation tensor with identity of V star, and the unit map is given by co-evaluation. So it is easy to verify that V tensor V star is a Q system. Okay, now so V tensor V star is a Q system. So now the question is whether every Q system in the category of finite dimensional Hilbert spaces is of this form or not. The answer is no. And one counter example is C power n, where n is not a perfect square. Okay, now let me give another similar example. So suppose C is any rigid sister tensor category and X be an object, and consider the evaluation co-evaluation maps. And now recall that R and Albert satisfy these equations. Now, just like the previous example, it will turn out that X tensor is variable. Q system. Okay, now one thing I should mention that every rigid sister tensor category has a canonical dimension function, and by dx I mean the dimension of X.
Can I ask?
Yeah. So
did you from that evaluation to evaluation, not maybe is there
maybe.
One is from 1 to X.
Okay, yeah. So in the so you can take the co-evaluation map to be the R bar star. Yeah. So since you are dealing with sister tensor categories, so since the sister structure is there, so it will not be a problem. Yeah. Oh yeah. So every rigid sister tensor category has a canonical dimension function. So by dx I mean the dimension of this object X. So just like the previous example, it will turn out that extensor x bar is a Q system, where the multiplication map is given by 1 by root dx times 1x tensor r star tensor 1x bar, and the unit map is given by r bar. So this becomes a Q system. And I have already discussed that not every Q system is of this form, right? Now, in this paper, the authors introduce the notion of Q system completion to characterize those sister two categories in which every Q system is of this form. So if a Q system is of this form, we say that the Q system splits. And if in a two category, if every Q system splits, then we say that the two category is Q system complete. And my goal is to show that the two category of unitary connections described in part 1 is Q system complete. And the title of this paper is Q system completion of sister two categories. So now let me formally define Q system completion. So suppose C be a start two category and X be a one cell from A to B, then a unitarily separable left dual for X, the dual X bar along with evaluation and coevaluation maps such that evaluation composite evaluation star is identity of 1A. Now, given such a unitarily separable left dual for X, just like the previous example, it will turn out that X tensor X bar becomes a Q system. Okay. Now, given a start to category C, it is said to be Q system complete if every Q system in C splits. That means, given a Q system Q from B to B, one can find an object or a zero cell C and a dual as well one cell X from C to B having an unitarily separable dual X bar such that Q is isomorphic to X tensor X bar as Q systems. Okay. Now, so to show that UC is Q system complete, the following steps are needed. So the first step is to build a new suitable zero cell in UC, and this is achieved by applying the realization functor psi on the given Q system. The second step is to build a dualizable one cell X dot W dot in UC, having a unitarily separable left dual in UC. And the third step is to build natural isomorphisms gamma case between xk bar xk and the functors that will appear in the Q system in such a way that gamma case intertwine the algebra maps and satisfy exchange relations eventually for all k. So we have this result that now before I stop, let me discuss some questions related to this work that are currently occupying my attention. So I just stated that UC is Q system complete, right? So now the natural question is whether the two category of unitary connections, whether they will also be Q system complete or not. And the second question is related to the peripheral Poisson boundary of UCBM. So I have some time, right?
Sure.
Yeah, okay. So let me briefly explain the notion of a peripheral Poisson boundary. So suppose M be any one dimensional algebra, and say P be a normal UCP map from M to N. Then the peripheral Poisson boundary of P is defined as the sister algebra generated by the set of all maximal eigenvectors of P. Now, the loop operator that I described in part 1, they give rise to certain UCP maps between certain one-dimensional algebras. I won't go into the details today, so we can talk about that later. So I plan to investigate the peripheral Poisson boundary of that UCP map coming from the loop operator. So I stop here, and here are the references. So the stock is mainly based on these two papers. Okay. And thank you for your attention.